Beyond semantic features, pixel level mapping for generalized AI generated image detection. So that's the name of the paper we're going to look into today. This paper cited my old paper, and hence I got a notification. So in this Decode Papers with AI series, we're going to use AI tools to try to understand what a paper is about. So let's jump right in. So as always, the first tool that we're going to use is Saral AI, and you can access that tool, saral.democratizeresearch.in. And the first thing you do is Saralify. So what Saralify does is that it can convert academic papers into engaging video presentations, slides, and other formats. So I'm going to click on this. First step is just to sign in using a Google account. And when that's done, the next step is you can just do some initial configuration. So you can configure your own API keys, or you can just use the system keys. So I'll just skip now and just use the system keys. Then I'm going to upload the paper that just cited my work. So it's called Beyond Semantic Features. Right. So I got a notification for that. So the paper is now uploaded. So what I'm going to do now is I'm going to try a few different formats here. So the first format I'm going to try is process PDF, right? So this is going to give me, it's going to process the PDF, and it's going to give me some information about it. So in the meantime, what we'll do is, this is the paper I was talking about, Beyond Semantic Features, Pixel Level Mapping for Generalized AI Image Detection. So it's about 15 pages long. In the meantime, this is done. So it says, okay, this is what it does. It says, it gives you the title, it gives you the author name, and then it gives you the publication date also. Maybe it took it from the paper, yes, 19 December. So what I'll do is I'll just say continue to scripts. So now what's going to do is it's going to generate a script for a slide deck / a video, and let's just wait for this to happen. So that's done. So this is what it meant by script. So what it's going to do is you have an introduction, methodology, results, discussion, and conclusion. So it's broken the paper into these 5 sections. And we can also select an image here if you want to just upload some images from the paper onto these slides, right? So, for example, I'm in the introduction section. So if I go back to the paper, let's see if there is so this is what they have in the introduction section. And this is the visualization results of they have something here. And then they have also, this is the methodology, overall methodology, and then results and so on. So let's try to see if I can maybe have a few images based on the paper right here. So I'll put this in the introduction section, just like what it did. And then I'll go to the methodology. In the methodology, I'll try to select the big picture, one of the ones which had the block diagram. I think this is the one. Yes, this is the one this is the second image we saw, right? So this is not the one. Original, high frequency. So maybe this should come in the introduction, because it was there on the second page. So I'll go back to methodology and I'll say change image and try to see if any other images are there. So far I'm not able to get the image that I saw earlier, but this could be the image. Yeah, this is the image which was there in the methodology, right? And then results. So when you come to results, could just pick one of them. Maybe I'll pick this one, and some discussion and conclusion, right? So I'll just not disturb these parts. Now what I do is now I have, if you see, 5 slides: introduction, methodology, results, discussion, and conclusion. I'm going to say save scripts, and I save the scripts. So next, it will allow you to go to a PDF or a PPT. So I'll just select PDF since it's just easier. PPT is you select if you'd like to make more changes to the PPT in case we want to use it for a presentation or other kinds of things. So it says generating slides. It's generated. So what we have here is, let's go and see all these slides one by one. So it has the first slide, the second slide, just like all the images that we selected are now here, right? So now I can download this PDF if I need. So let me just quickly download then, so that I have some quick information about this paper. It has basically compressed the paper into this kind of information. And now what I'm going to do is I'm also going to say continue to audio and video, so that it starts generating the audio. So I can select which female or male, and then I say generate audio. So yes, so this is what is happening. It says, okay, it's going to narrate and it's going to generate the slides. Then it's going to package the audio files and then final video file. In the meantime, let's look at the paper here, right? So let me try even going through the abstract first. That may give you some kind of information. It says the rapid evolution of generative technologies needs reliable methods for detecting AI-generated images. A critical limitation of current detectors is their failure to generalize to images for unseen generative methods. This is very true. I've seen it from my own research. It works well on the data set they provide, but if you wanted to generalize beyond that, it's not going to be that easy. To overcome this, we introduce a simple yet remarkably effective pixel level mapping pre-processing step to disrupt the pixel value distribution of images and break the fragile, non-essential semantic patterns that detectors commonly exploit as shortcuts. That's a mouthful. It says a simple yet remarkable effective pixel level mapping pre-processing step to disrupt the pixel value distribution of images and break the fragile, non-essential semantic patterns that detectors commonly exploit as shortcuts. And then this forces the detector to focus more on fundamental and generalizable high-frequency tracers. And then it says through comprehensive experiments on GAN and diffusion-based generators. They say that the method has good cross-generator performance with state-of-the-art detectors and so on. So that was interesting. Okay, this one is also done. Okay, that was pretty fast. Like I just read the abstract and this is done. That's so super fast. And let me also download the video so that I have a copy of this. And what I'm going to do now is that I'm going to start playing the video. So it has kind of created a 3-minute video of the whole paper based on the scripts that it got from the paper, and then also the images that we selected, right? So let's see what it says.
Welcome to this presentation on Beyond Semantic Features, Pixel Level Mapping for Generalized AI Generated Image Detection. This research was conducted by Chenming Zhou et al. And published in 19th December 2025. Today, we'll explore the key findings and contributions of this important work. Let's begin by understanding the problem this research addresses. The rapid advancement of generative models has led to AI generated images that are nearly indistinguishable from real photographs. While beneficial for creative applications, this advancement poses societal risks due to the potential for misinformation and the erosion of evidentiary reliability. Existing AI generated image detectors often perform well on images from known generative models, but struggle to generalize to unseen models. The problem of detecting AI generated images is framed as a binary classification task. The objective is to train a classifier on images from non generative models that can effectively identify images from unseen generative architectures.
So let me pause here, and if we go back and play the previous slide. So what we see here is that, so usually what happens is, can it generalize on unseen generative models? Can AI image detectors, fake image detectors, right? So, for example, I think here they have a high frequency filtering and then some shuffling and then some shuffling. You can see how these two are very different, the detectors, whereas here their method kind of maybe is picking up on some better cues, right? And then if we go further down, I think
Same generative architectures. This requires both intra-class generalization across different architectures or training variations of the same model family and cross-class generalization to different model families like GANs and diffusion models not seen during training. Comprehensive experiments were conducted to evaluate the proposed pixel level mapping method on the to different model
let me
families.
pause here and then I'll just try to again understand this thing. So there is a fixed pixel level mapping, and then there's also a random pixel level mapping. So they try to maybe map this to a different, from this RGB image, there is a mapping module which maps this to a different image, and this image looks like completely different, right? It's no longer in the space of natural images. It's in a completely different, looks completely different. It doesn't look like a natural image. And you can see that from here that the range now is different. So usually natural images are grayscale images with unsigned integer RGB arrays. So it's from 0 is black and 255 is white. So I think if they're claiming that they're just mapping this to a completely different map, like one negatives and so on, and then so basically RGB, all the RGBs are mapped to like three different thing, and then they apply some detectors. That seems like too simple and crazy, but if it seems to work, that's amazing. It's pretty cool if that's what they're doing. So let's go further down.
Models not seen during training. Comprehensive experiments were conducted to evaluate the proposed pixel level mapping method on the self synthesis GAN dataset. The method significantly outperformed existing approaches, including the state of the art NPR, by 4.7-inch classification accuracy. Similarly, on the GAN image dataset, which includes high resolution images from state of the art diffusion models, the method achieved a new state of the art accuracy of 98.4, surpassing previous benchmarks by a significant margin. The experimental results strongly support the effectiveness of the pixel level mapping approach in enhancing the generalization capabilities of AI generated image detectors. The significant performance improvements observed across diverse GAN and diffusion models highlight the method's robustness. The analysis suggests that the key to generalization lies in shifting the focus of the detector from brittle semantic cues to more fundamental, high frequency, generative artifacts. This paper introduces a novel pixel level mapping preprocessing step that significantly enhances the generalization capabilities of AI generated image detectors. By transforming pixel values, the method effectively suppresses low frequency semantic bias and amplifies high frequency generative artifacts. This computationally efficient approach allows detectors to focus on more robust and generalizable forensic traces inherent in the image generation process.
That's it. And was a quick summary, so that was good. So the method seems to be super simple, and if that works, that's amazing. So what we'll do next is that we have a quick video summary. Let's maybe try out a few more different formats and try to so as we kind of see these other formats, the hope is that we get better and better understanding of the paper, right? Let's do like that, just that. So we are back, and I uploaded the paper, and we just saw what happened when you did process the PDF and generated a video. So now what I want to do is I want to try these things. I'm going to click on one-click poster. So this is going to give me just a quick one slider, one click of everything about the paper in just one slide, so that I can quickly glance over it and get a quick overview of that as possible, right? So let's see how long this takes. It's been 15. My guess is that it should not take, oh, that's it, 20 seconds maybe. That was amazing. That's like super fast. I hope it generated some nice posters. Yes, it did generate something. They're not pictures, but it's fine. So it says beyond semantic features, pixel level mapping. It has all the authors. So it says, if you come to the abstract now, it says current AI generated detectors struggle to generalize. We saw that. We introduced a novel pixel mapping pre-processing step. We also saw this. That disrupts monotonic pixel distributions to suppress low frequency semantic bias. So achieve state-of-the-art performance across GAN and diffusion-based architecture, demonstrating that breaking semantic shortcuts is key to cross data detection. So next, if you go to the introduction, it says the rapid evolution of GANs and diffusion models will produce photorealistic synthetic images. Existing detectors fail to generalize. We demonstrate that current semantic reduction methods like high-pass filtering and patch reshuffling are insufficient to prevent deep learning models from exploiting semantic shortcuts. So then, as I say, we propose a pixel level mapping module that transforms original pixel intensities to disrupt low frequency spatial arrangements before the image enters the classification network. The fixed mapping uses a deterministic function to amplify adjacent disparities while normalizing values to a range that facilitates effective classifier training. So this is an interesting statement. And then a random mapping variant applies independent transformation tables to each image channels to prove that the disruption of monotonic pixel order is more critical than specific mapping rule. So that was interesting. So this is the best part, the results. So our results provide a computationally efficient solution to generalization challenge by forcing detectors to focus on universal high-frequency traces rather than semantic bias. Extensive validation across GANs and diffusion architectures prove it's really good. Further future research will investigate the synergy between pixel level intensities and large VML. Thank you. So then I think that's it, right? So that's good to see. This was again a quick overview, all in one slide, and they also have some nice references here. And okay, there is also a results part. I think we skipped that. It says our approach achieves a new state-of-the-art average accuracy of 98, significantly outperforming established baselines like C2 UniFD and C2P CLIP. The method demonstrates superior cross-generation generalization of the self-data synthesis data set. Then qualitative spectral analysis confirms pixel level mapping equalizes frequency energy distribution, exposes hidden checkerboard artifacts, which are there in the resampling process. So this one, I think we understand some of this, but it would be good if we go more into the paper and read it in a better way. So let's do one more format before moving on to the next AI tool. So I'm back and I uploaded the data set in the PDF in Saral. And this time we saw a video, we saw a poster. So this time what I want to do is generate a one-click podcast. So I'm just going to select English and then say generate. So what this will likely do is that it's going to take the paper, convert it to an engaging podcast presentation. So in the meantime, this is going to take a while. Maybe it says it takes under 2 minutes. I hope it finishes faster than that. So we are still not like say it's 11% complete. So I wonder what the mapping is, right? Like it says do a pixel level mapping, and then in the diagram we saw like a different range. Is there a rule to this mapping? So all of these are interesting questions to actually know about. So one of the things that is that it says it tries to generalize. So how generalizable is this method? Like has it done on a large thing? So something is going on here. So let's do it again. So the podcast is now completed. It's generated another almost 4-minute podcast. So let's listen in. Just to make it faster, I'll just change the speed to 1.25. So let's listen to the podcast.
Hey Rohan, ready to dive into this AI generated image detection paper?
Totally, Aisha. Sounds like a Wild West situation with all these fake images popping up.
Exactly. The paper talks about how current detectors are easily fooled. Why is that?
Well, they overfit. They learn specific quirks of one AI model, not general fake traits.
So it's like recognizing a specific brand of fake, not just that it is fake?
Precisely. They focus on semantic cues, things that give the image meaning.
Okay, like textures, blurry bits, weird colors?
Yep, those visual artifacts. But those change with each new AI model.
Makes sense. So how do they try to fix this overfitting problem?
They introduce pixel level mapping. Sounds complicated, right?
It does. What's pixel level mapping actually do?
It messes with the image's pixel values directly, disrupting those semantic cues.
So scrambling the image in a way that hides the tells?
Kinda. It breaks down the obvious patterns the detectors usually latch onto. Is again version ID.
And by doing that, the detector has to look for deeper, more general signs of AI fakery?
Bingo. High frequency traces, tiny details inherent in the generation process. Why?
high frequency like super fine textures or patterns?
Think of it like the difference between a smooth surface and a slightly bumpy one.
Got it. So they're forcing the detector to see the bumps that all AI images share? Uh,
Exactly. And how well does this pixel level mapping work?
Apparently, it significantly boosts the detector's ability to spot fakes from unseen AI models.
So I really like the analogy that is given, right? Although it may not be the completely correct one, but just to visualize and understand this analogy is great. So it's safe to say that natural images are usually low frequency, like smooth. And in this paper, they're doing a pixel level mapping, which tries to take the image and like put it to somewhat like high frequency. That's what we saw. It was completely like noisy when we saw those mappings, right? And the analogy it's trying to provide is that like you can imagine a smooth surface versus a surface or road with lots of bumps. So the smooth surface, you can imagine that to be an image, and the one with bumps, um, that one is what is like what the high frequency ones are maybe showing, and they may not be visible to humans, but the AI image detectors are hopefully like trained to detect them, right? So when we see, for example, when we I can't see any bumps or anything here and here, but maybe an AI image detector which is trained can actually like find that. And they're saying that this really boosted their accuracy, so it's really interesting.
That's the key. Cross-generator performance. Generalization is the goal.
The paper mentions GANs and diffusion models. Are those the bad guys here?
Haha, they're the generative models creating the fake images. Yes, different brands of fakes.
Okay, so they tested their method on fakes from both GANs and diffusion models?
Yep, and it worked well on both, showing it's not just a one-trick pony.
So, what's the core idea they're trying to prove with all this?
At disrupting semantic cues, the easy-to-spot tells is key to generalization.
Less focus on the obvious, more focus on the fundamental fake.
Exactly. They even compared their method to other semantic reduction techniques.
Like what? The paper mentioned Fourier transforms and patch shuffling. The
Right. Fourier transforms remove low-frequency components, patch shuffling mixes up the image.
But the paper says those aren't as effective. Why not?
They either don't fully eliminate the semantic information or lose too much real information.
So, pixel level mapping is the Goldilocks solution, just right?
That's the claim. It reduces semantic bias without losing the important generative artifacts.
Makes sense. And it preserves local correlations of pixels, apparently.
Yeah, that means it doesn't just completely randomize everything.
So, less information loss and more emphasis on those high frequency forensic features?
Precisely. A win-win, according to the paper.
Overall, sounds like a really interesting approach to a growing problem.
Definitely. AI-generated images are only going to get more convincing, so we need better detectors.
This pixel level mapping might be a crucial step in that direction.
Agreed. It's about making detectors smarter, not just quicker to spot the obvious.
Well, Rohan, thanks for breaking down this complex paper with me.
Anytime, Aisha. Always a pleasure to talk science.
That was it. That was good. It provided some good analogies, and then all our formats together, the video, the poster, and this was really good. And then let's do this for a few more formats and few more tools to try and see how much we can get out of this paper just from AI tools, right? So for the last part, NotebookLM has created a 7-minute video from this paper. So let's just have a look at that.
Okay, let's just jump right in. We're in the middle of a visual revolution, right? AI can now cook up images that are so incredibly realistic, they could fool just about anyone. But that creates a huge problem. I mean, when you can't trust your own eyes, how do you find the truth? Today, we're going to look at a fascinating breakthrough in spotting these invisible fakes. You know, this quote from the research paper we're digging into today just nails it. This isn't just about making cool art online. It's about a potential crisis of visual authenticity. The very same technology that lets us create these amazing things is also threatening our ability to believe what we see. And the progress here has been absolutely staggering. I mean, think back just a couple of years ago. You could usually spot an AI fake by looking for weird stuff, like six-fingered hands or bizarre, distorted faces in the background. Well, those days are long gone. The tech has gotten so good, so fast, that we are in a serious race to build new tools just to keep. So you're probably thinking, wait, don't we already have AI to detect AI? And yeah, we do. But here's the mystery. They're starting to fail. And not just fail a little, but fail badly. And the reason why is really interesting. It's like they have this hidden blind spot that no one saw coming. The whole problem really boils down to this one word: generalization. Think of it like this. If you trained a detector to spot fakes from, say, Mid-Journey version 5, it gets really, really good at that one job. But what happens when you show it a fake from a brand new model it's never even heard of before? Well, that's the generalization test. And that's where everything just and you can see the problem perfectly right here. On the left, you've got in distribution. These are fakes from AI models the detector knows and was trained on. Look at that. Accuracy is through the roof. But on the right, for out of distribution, fakes from new unseen models, the performance just completely tanks. The detector is basically just guessing at that point. So why the massive drop-off? Well, researchers figured it out. Our current detectors have been taking a lazy shortcut. It turns out they aren't learning what makes an image fundamentally fake. They're just memorizing the temporary little mistakes of the current generation of AI models. These shortcuts are what the paper calls semantic cues. They're all the superficial tells, the little mistakes a specific generator makes. Maybe it's a weird pattern in how it draws grass, or a particular kind of blur in the background, or an unnatural glow around an object. The detector sees these easy clues and latches onto them. But it's not actually learning the deep physics of what makes an image fake, it's just memorizing easy tells. And this is the fatal flaw in that whole strategy. Because as the AI models get better and better, they fix those little mistakes. The weird textures, the odd glows, they disappear. And when those superficial cues are gone, the detector, which was relying on them completely, just goes blind. The rug is pulled right out from under it. So, to solve this, the researchers came up with this radical, almost backward idea. What if, to find the truth in an image, you first had to completely break it? This was the big question they had to answer. How do you stop an AI detector from getting distracted by the pretty picture, the semantic information, and force it to look deeper, to find the universal fingerprints that the AI generation process itself leaves behind? Okay, so take a look at this. This is a normal, high quality picture. It's full of what we call semantic information. You can see a flower, a background, different textures, colors. This is exactly what tricks our current detectors. They get so bogged down in what the image is showing that they totally miss how it was made. And now, this. This is what the researchers make the detector see instead. It's the exact same image, but it's been processed until it looks like a chaotic field of digital noise. The original flower, it's completely gone. By destroying the content, they've actually removed the distraction. This really powerful technique is called pixel level mapping. It's a simple step that happens before the detector even lays eyes on the image. It works by systematically changing the value of every single pixel. The goal is to just shatter all the recognizable patterns and, in doing so, amplify the hidden, almost invisible artifacts left behind by the AI generation. So let's break down how this actually works. First, the process scrambles the original pixel values. Second, this turns
So what I'm not understanding here so far, maybe from the previous one also, this, I understood this, disrupt, convert to noise and focus on the artifacts, but how are they doing it, right? This is the method, and it makes sense. But I don't know if maybe the paper talks about it, but from this video, at least I'm not able to understand how this is done, right? So that's one thing which seems to be missing from this, at least from this initial video. And because it's all the other things are like, yes, you can see that it'll shows the results will show, and then it's working, and when it happens this way, all of that is fine. But the how are they doing it is still not very clear from here.
trying to spot a forged painting. They don't just stand back and stare at the subject, the person, or the landscape. No, they get up close. They pull out a magnifying glass. They analyze the specific texture of the canvas, the chemical makeup of the paint, the unique way the brush strokes were applied. That is exactly what this method does for digital images. And this slide shows us exactly what the detector can now see. On the left, that's a real photo after being mapped. It's just random looking noise. But now look at the fake image on the right. Whoa. The mapping process has revealed this subtle but very distinct checkerboard pattern. This pattern is a direct fingerprint of the AI's creation process. It's a universal clue that's always there, no matter what the picture is of. And the results? Well, they really speak for themselves. This chart compares, so what this all means is that we're looking at a fundamental shift in how we have to approach this problem. The future of spotting these fakes isn't about looking for flaws in the content of the image anymore. It's about doing the forensic analysis of the creation process itself, finding the invisible tool marks that the AI leaves behind. And this really leaves us with a bigger question, doesn't it? This whole method teaches us to look past the obvious, to find truth in the underlying structure instead of just the surface. So as AI gets more and more woven into our world, how else will we need to change our own perception? How will we have to learn to see differently, just to figure out what's real?
So we're at the end of it. So I would say that I was not too impressed by this one. Usually NotebookLM videos have been more impressive because, I mean, first of all, I've seen from the previous versions what all previous formats, what the paper is trying to do. But this one, like, never talked about what the actual method is. It just says that this is what it tries to do and these are the results. So that's pretty surprising. The first time I'm seeing it like that, right? So we're going to go back to the paper now and try to see if I can understand by myself what it's trying to do. So let's see the important contributions, right? We demonstrate that high-pass filtering and image patch shuffling failed to effectively eliminate semantic information. So we introduce a novel pixel level mapping method that attenuates semantic bias during classifier training by transforming low frequency information on amplifying high frequency artifacts. Our method reduces classifier reliance based on semantic features, extensive validation across multiple benchmarks affirms that, right? So let's go further down. So I go here, interclass. So these are just classification things. So this is what we saw earlier, right? The input image first passes through the pixel level mapping module before being sent to the classification head. The fixed pixel level mapping, in this is B, the fixed applies the same fixed level mapping to all three channels. So you can see that from 0 is 0 to 255, it's changed to 0, 1, minus something, minus 0.56 and all of that. So the range and the negative values are introduced and so on. And random pixel level mapping, the random applies a different random mapping to the three channels of the image. So here all the RGB undergo the same transformation. Here B underscore one transformation, G underscores another one, and so on. So this is very interesting. So it says, given an input RGB image I, which belongs to real numbers, height, width, and 3 by 3, with pixel level 0 to 255, a mapping function that amplifies the differences between adjacent pixels while normalizing pixel intensities to facilitate classifier training. So it says amplifies the differences between adjacent pixels, right? So they say that for each pixel V, which is like 0 to 256, actually, yeah, 0 to 255, it says phi f of V equals V minus round of V by 256 comma 2 times 256, right? So V is the original pixel intensity and round is the numpy round, and with decimals equals to like 2. So the selection of decimals aligns with monotonicity disruption principle. So it's like I think like they want to okay, I'll just look further into it. Setting decimals equals to 1 preserves linearity due to coarse quantization. 1 by 256 equals 0.39. With decimal greater than 1 disrupt monotonic arrangements, and decimals equals to 2 simultaneously normalize the transform pixel values to the range of, okay, so they have this range also, minus 1.28 to plus 1.28. So they also shift the range this way. So you're going to get floating values now, decimal and floating values now. So that's another interesting thing. So what we see here is also like a rounded version, right? It's although the actual is it's going to be float. So it's going to be like phi f of v is probably going to be like floats now. So for example, if I have a number 0, if pixel intensity is 0, so this will be minus round of 0 by 256 again going to be 0. So this is going to be like everything is going to be 0. If it is say 1, so it's going to be 1 minus round of 1 by 256 comma 2 times 2 to 6. That's what it's going to be, like a small value, a decimal value, either positive or negative. So it says one, for example, 1 by 2 to 6 is 0.0039. So but if you have a 2, so that's going to be like slightly different. So now it makes a little bit more sense, and I can see how to even programatize this in say Python or any other language. So this was what was missing in the NotebookLM video explainer. So it would have been great if it had also like explained this. And so I think, and it's fascinating to see that such a simple method is actually able to give some really good results on this, right? So this is what I think I wanted to know from this whole part, like kind of. That's nice. So I think that's the end of this video, and it was great to see this paper is using a simple method, and I tried to like get really good results, and also generalizability in AI fake image detection, and just using the simple mapping of pixels from one range to another range using mapping functions. And they tried both in RGB as well as random pixels, random mapping in each of these channels to show like how good their method is. So I think like if it could, this could be a great I think like if it works out to be true, one of the major breakthroughs in this field is if you can do these mapping and then learn better features and then go with it. And maybe even this would be used in videos for deepfake detection, a similar method, right? Videos also have a similar mapping, and you also have time there, and maybe you can apply similar mapping functions to videos and try to detect those artifacts which cause video deepfakes. So I think this was a fascinating paper, and AI did help me. So I would also strongly encourage you to take take this paper and apply more AI tools. In fact, I was so curious that I went ahead and tried a few more formats, and tried playing around with it to see what is actually happening in the paper. So the results were pretty good. But in view of time, I'm not sharing those. But would strongly encourage to try that and see what this paper is about. So until next time.